Hello and welcome to Buildings of Tomorrow. My name is John Lester, and in today's episode we are talking about fire safety in gigafactories, in factories that we produce batteries and battery cells. I'm joined today by two guests. I'm very lucky to be joined by two guests today. Emelie Emanuelsson, who is Global Product Manager for Fire Safety Applications at Siemens Smart Infrastructure, and Manuel Obert, who is an expert for structures, seismology and fire safety at TÜV SÜD. Emelie and Manuel, thank you so much for joining us.
Thank you.
Thank you.
And before we jump in, Manuel, could you give us a quick explanation on TÜV SÜD, where you're representing today? Who are you and what do you do in our industry?
Of course, I will. So let's start with my company, TÜV SÜD. So TÜV SÜD is a trusted partner of choice for safety, security, and sustainability solutions. So today, TÜV SÜD is represented by more than 25,000 employees located across over 1,000 locations worldwide. And I, as a person, work in the Department of Structures and Seismology and Fire Protection. And as an example for this topic today, I am also a project leader. I was a project leader of the technical report we are talking later about.
Perfect. Emelie, a quick question for you. In the title, I mentioned gigafactories. What does gigafactory mean?
So gigafactory is a common name for large factories that nowadays are producing lithium-ion batteries. And giga means basically big. And to give you an example, the new factory that Northvolt is building in the north of Sweden equals the size of 70 soccer fields. So these are huge factories.
7-0 soccer fields.
7-0 soccer fields. So we're talking about large factories, gigafactories.
Wow, that's amazing. And this, as you say, this is something that is quite a common term now. We're starting to see this more and more in industry press, in normal press as well. Why are we starting to see gigafactories so much more today than we did in the past years?
So especially here in Europe, we're seeing them popping up almost in every country right now. It is basically to be able to have production close by for the automotive industry and providing renewable, clean and green energy as well for the power generation. And I would say it's also a consequence of trying to meet the Paris Agreement that we see right now, that Europe is investing a lot into gigafactories and the possibility to have green energy close by.
Right. So e-mobility, those consumer electronics that you mentioned, all leverage this technology, and that really driving factor of the localization that we see is that requirement to have manufacturing close to where the usage is and to push this. Perfect. And maybe quickly before we dive into a little bit more depth of the fire safety applications, you mentioned before that these factories are huge. Mm-hmm. What else is special about them, that make these gigafactories a bit different from some of the more traditional industries we know?
Well, I would definitely say that the most remarkable thing when you build such a huge factory like 70 soccer fields right now is that they try to be powered by green energy. So located at places where you have green energy close by, that's one thing. And the other part of it, and now I'm primarily talking about the European ones, is that they also want to have then recycling facilities for the materials and the used batteries close by. So like closing the ecosystem of the whole chain here of batteries. This is maybe a bit different from what we have seen in other areas of the world. That is special. The size, the clear focus on sustainability, the clear focus on providing green energy and renewable, recycled whole ecosystem.
Amazing. Thank you for that, because I think it's, as you say, that's something that's relatively unique when we look back into the past rather than this sort of global supply chain approach. They're changing this cyclical approach into a local supply chain, which is a big shift, especially for this kind of industry when we talk about mobility and things like that.
Yeah, and I think, for example, there are also it's driven all by the automotive industry, and they are also committing themselves then to have green policies. So if you buy a car in a couple of years, the consumer might want to know that the whole vehicle is certified green and that every part of it was recyclable. So it's a shift here.
Yeah, absolutely. Let's dive into the process itself a little bit. Manuel, what is the process that is used to create these battery cells, and which parts of it kind of highlight or deliver the highest levels of risk from a fire safety perspective?
Yeah, well, a lithium-ion battery, or shortly LiPs cell, can be produced in 3 different variants. To start with some basics, there are cylindrical, prismatic, or pouch cells, but independent of the type of the cell or of the production process, this production process is divided in 3 high-level process steps. So first there is the electrode manufacturing. Afterwards, it's going on with the cell assembly, and at the end there is the cell finishing. And from a safety-oriented point of view, the 3 high-level process steps can be divided into 2 hazard zones. So the first one is all the process steps during the electrode manufacturing and cell assembly. In these steps and process steps, there are no electrochemical hazards active. The hazards only exist due to process steps itself or the intrinsic material properties. The second hazard zone, it's the most important one, it's the cell finishing. All of the process steps during the cell finishing. So as soon as the battery cell is filled with electrolyte, a potential of electrochemical hazard is given. And therefore, the cell finishing is allocated to the highest risk potential during the whole production process.
Yeah, perfect. Let's take the chance to dive in a little bit deeper then in this cell finishing process. As you mentioned, this is the part of the process which is the highest risk. Within that high level process, what are some of the steps that really deliver this high risk from a fire safety perspective?
So within this cell finishing process, the high level process step, let's say, there are 2 key processes that represent the highest risks. The first is the formation, and the second one is the aging. Let's start with the formation first to explain a bit more about the process step. During the battery formation, this is the process where the initial charge and discharge of a battery cell is occurring. So let's say it's kind of when the cell comes to life. And this can take several days up to 1 or 2 weeks. When you're talking about the hazards within this formation process step, with the start of the first charging cycle, so the production errors from previous process steps can have potentially very dangerous consequences. And as several cells are charged and discharged at the same time, there's also increased risk of fire due to the large quantity of cells. So that's again, considering all the production process steps, the formation process is the one with the highest risk potential. As I said before, it's the first time the cell is charged and discharged and checked for the first time if there is a current or not a current active. So that is related to a very high risk, and electrochemical hazard is available. In addition to this, the arrangement of the cells, they are like stored during the formation process in formation tower or in racks in close proximity. That also contributes to this risk classification. The second process step that is allocated to a high risk potential is the aging process. And this process presents the final or represents the final step in the cell production and is used for quality assurance. And again, also during this process, a huge number of cells, we are talking about 10,000, 100,000 of cells, are stored for a longer time. This could be up to 3 or 4 weeks in a high bay storage area. And within this process step, the cells undergo different phases, which are separated by temperature. So the cells undergo high temperature aging and normal temperature aging. Now we're coming to the hazards during this aging process. During this process, there is no real-time voltage and impedance measurement carried out. So a so-called thermal runaway might be difficult to detect. And obviously, cells with a previous damage may subsequently become conspicuous during the formation process. But there is still a low probability that a cell which has survived the formation process before will become conspicuous during the aging process step. And however, due to the very large quantity of cells, which I said before could be 100,000 and more, in the aging process, it still exists a considerable high fire risk in this step. So there is also appropriate actions needed to be taken.
Okay. So within this cell finishing process, you described then two specific steps, and thank you for that deep dive, because I think it's an important step of this conversation. There's the battery formation, and I like your description. This is when the battery first comes to life. It's the first time that battery is charged and discharged. Highest space of risk because this is really the first time that any manufacturing issues could come up. And then you had the aging process where after a cell has gone through this formation process, it's then stored over a certain amount of time. And in both these stages, like you described, we have a lot of cells in close proximity. So if we have a challenge with one, we risk that issue moving forward, whatever it might be. You mentioned a phrase there, thermal runaway. What does thermal runaway mean?
Thermal runaway is a very common expression in this kind of field. Battery cell production, and it's also the most fundamental and most important, let's say, most critical hazard. So thermal runaway is an exothermic chain reaction that starts when the heat generated within a battery or battery cell exceeds the amount of heat that is dissipated to its surroundings. So if the cause of excessive heat creation is not remedied, the condition will worsen and worsen and worsen. So the internal battery temperature will continue to rise, causing battery current to rise, causing temperature to rise. That's why it's called a kind of a domino effect, which can at the end lead to catastrophic results such as fire, explosion, sudden system failure, costly damage to equipment, and possibly personal injury. So the rise in temperature in a single battery cell will begin to affect other cells in close proximity, and this, let's say, pattern will continue, thus the term runaway. So yeah, in the expression thermal runaway.
Perfect. Thank you for that, because I think anyhow, very shortly, Emelie will talk in a little bit more detail about what we can then do about this if we ever find ourselves in that situation. But I think it's an important one, as you say, because it is relatively unique to this industry and the chemical reactions and risks that are synonymous with it. Manuel, if I was someone in the industry looking to build one of these gigafactories, so I had the goal to go ahead and do this. You just described some really significant risks that not just risk the quality of the product, which is then finally delivered, but actually, the whole production process and the safety of those people involved in that. How do I go about this? If I was building one of these factories, how would I go about addressing these risks?
Yeah, well, let's start first with the conventional, let's say, fire safety. There are existing a lot of generally very clear regulations to ensure safe and qualified fire protection. But for the LIP cell production, there are currently no codes and standards available or protection concepts in regards of the fire protection measures. For this reason, we collaborated on a technical report together. It was us as TÜV SÜD and you, Siemens, with co-production of the University of Aachen. And this technical report should be seen as a general guideline for fire protection strategies in the field of LIP cell production. So based on, let's deep dive a little bit into the topics or the content of the technical report, based on a generic description of the different production process steps, which I mentioned just before, or highlighted the two steps during the self-finishing. We just described the hazards and allocated the hazards to each of the process steps. So we identified 16 process steps. And then with the help of an appropriate risk assessment, the risks are allocated to the hazards described before, or the hazard to the risks. These two words are linked to each other. So, and then on the basis of this risk evaluation, the best fitting fire protection measures mitigating this risk are defined and described to present a thorough and generic solution with respect to the structural, technical, and organizational fire protection.
Understand. So for normal fire protection, we have a lot of regulations. We have a lot of expectations that are set by the industry on how to best protect. We're not quite to that point yet for this specific industry, and this is why you described this technical paper, which we'll look into in a little bit in some more detail. What are the benefits of taking this approach, of taking a risk-based fire protection approach?
Yeah. So generally, the codes and standards which are implemented for fire protection measures, they cannot be applied entirely case or plant specifically, which means there is always a potential of over-fulfilling the fire protection measures in regards of the specific plant. And by using a risk-based fire protection strategy, the costs during planning and implementation of fire protection measures can be minimized considerably, as this is the most efficient and effective tool in a so-called performance-based environment.
Wonderful. Thank you very much for that. And Emelie, thanks for sticking with us, because Manuel just took us on a great deep dive into the process, the specific steps within the manufacturing process that provide the most hazards, and then how those hazards are then connected together with the situation to create a bit of a risk assessment, and the process that you've gone together so your team and his team and the University of Aachen to create this report. Let's talk a little bit about our reaction once if we found ourselves in the situation of a thermal runaway like we talked about before. What can we do about it? What can we do from an extinguishing perspective to really manage a thermal runaway situation in a lithium-ion battery cell or in a manufacturing situation like this?
So first of all, I hope that we have so good detectors installed that we will never end up in a thermal runaway to start with. But if we would end up having a problem, on our side, we are proposing to use an inert gas solution, because there is no extinguishing agent really that can stop a thermal runaway in this kind of applications. So you have to imagine like huge racks, and there are quite big openings, and it's really about suppressing the fire as much as possible, and as Manuel talked about, to remove the faulty cell or the burning cell away from that and put it into a safe zone with water and so on. But what we propose on our side is a nitrogen system. We know in the market right now that a lot of OEMs in this field are proposing a Novec system with like a Novec 1230 system, which is a chemical. We do not do that because it will leave a lot of residues on the battery cells themselves. So we propose to suppress as much as possible with a nitrogen system that will create an inertization and stopping the thermal runaway to spread at least.
Yeah, I understand. And I'd like to, and thank you for that first point. Like, of course, detection is that first step, and as best we can do this. This is our first line of defense, let's call it.
Yes.
And then if we do reach the point where we do have a thermal runaway, keeping it as much contained as possible until we have the chance to physically distance, the cells where this is occurring, and get them away from the thousands of other cells that are in the racks in the towers, like Manuel described for us before. Is there things like a uniform approach, a standard approach, a standard methodology for fire safety being created, at least here in Europe as an example, to address this kind of gap that we have in the current regulations and expectations?
No, not really. There's an industry association called Euro Alarm, and they're working on guidelines for this protection. but there is no formal legislation from the European Commission yet.
Okay.
You can look at the EU directive, the machinery directive, if you consider this as machines, of course, and it needs to be safely operated. But that would, for example, propose a water extinguishing system. And not so for the machines, yes, but not for the safe operation and the process which we are aiming at.
Understand. Which brings me back again to the report, and one of the main reasons we're having this conversation is, that we have an industry that's expanding so quickly. We have an application which is in huge demand, but is 100% going from something we didn't hear about or wasn't really part of what we were doing here in Europe, at least on a scale 10 years ago, and now one of the biggest things which is happening in the industry. We need to ensure that as an industry we have the awareness and we have some understandings and we share that best practice so that we can build the most future-proof and safe and capable factories moving forward. And this is one of the main reasons, or one of the many reasons, I'm sure, that TÜV SÜD, Siemens and the University of Aachen worked on this technical paper and the white paper that goes along with the technical report, sorry. Mm-hmm. Where can we find these, Emelie? If we were looking, a listener here wants to know more, and there's a huge amount of detail and technical information, like Manuel mentioned before, in the technical report, and some information also in that white paper. How would I go and find this? Where would I search, and what would I search for to find this technical report and the white paper? So
I think Manuel needs to answer for TÜV SÜD, but from Siemens side, I think the easiest way is to go to siemens.com/battery, and they will get to a page gathering information about everything that Siemens do when it comes to battery production, and there just type "contact me" and write "I want a report." That's the absolute easiest way.
Yeah, the same for TÜV SÜD. We also created a landing page where you can find the report and the white paper. And also you can listen to a virtual conference that took place in June. So where also Siemens was involved. It was a speaker available from Siemens during this virtual conference. But all these documents are concentrated on our landing page at TÜV SÜD too.
Perfect. Amazing. Thank you so much. And thank you both for lending us your time and your expertise. As I mentioned, the technical report and the white paper are both extremely detailed and such an important step forward in supporting the industry in general, in addressing this significant risk in a piece of the industry, in a part of the industry which is just growing at such an exceptional rate that we have a lot of decisions, we have a lot of colleagues and collaborators across the industry that we need to get on board with this whole conversation and make sure that we do create a safe space. So thank you so much for that, and thank you so much for joining us this afternoon.
Thank you.
Thank you. It was a really great pleasure for me to participate in this podcast episode.
Same here.
And a great pleasure to have you both here. Exactly as Emelie and Manuel mentioned, if you head to TÜV SÜD or to siemens.com/battery, find these technical reports, find these white papers, feel free to reach out. And there's also the opportunities there to get in contact, I'm sure, with some of the experts and continue the conversation. So until then, please feel free to go and do that, get hold of that report. Otherwise, keep an eye out for our new episodes. And before you know it, we'll see you again soon with the next topic. Thank you.
Thank you.
Thank you. Bye.